Lab 10 then looks at the chi-squared test. Uh, Now, this is properly called the chi-squared test of independence. And we'll see why this is, but one of the simpler things about it is that we don't have to think about the direction we specify the test. But it also has some limitations that we will go over in this lab. Now, I've already loaded in the data. I've got this Uber data here. Now, this is the first lab that looks at this, so we'll just have a quick look through. Now, what this is information from different Uber dispatch companies on the number of active vehicles and the number of trips per day for multiple companies in the months of January and February. So this is going to provide us with both some continuous and categorical variables. And actually, we're going to use this for the chi-squared test, for ANOVA, which Lab 11 looks at, and indeed for linear regression in the final lab. Now, this lab starts with a little bit of recoding and also a bit of loading packages. Tidyverse, this is the one that we normally use, but you can see here as well, we've got a second package called RCompanion, and this is going to be for what we call post hoc tests, which in this case is going to be the pairwise test of nominal independence. And again, we'll see how that works a bit later on in this lab. So we load in the data here. And the first bit of this lab is just a little bit of recoding. Now, I won't go through most of this. We're just turning the month variable into factors here, using factor. The interesting one is this. So we also have as a vector type as date, because as we can see in this data, we have a date column. And dates are a little bit difficult to handle as data sometimes, because although year is effectively a count of years, months and days are a bit irregular. So we have 12 months in a year and irregular numbers of days in a month. So in order to be able to say sort of what is the difference between this day and this day, so we would look at that and know it was 3 days, R needs a little bit more information. And we do that with just like as factor or factor. Here we have as date. And we just need to tell it, which variable we want to use. In this case, that's date. And then we use the format of the dates. So these dates are year, month, day, and they have dash separators. So we can just run that. And in fact, if we glimpse, then we can see that the vector has changed to date. Now, once we do that actually as well, if we run this, we can then run this, weekdays. So because this is a date, R can now tell us what day of the week it was on that day. So the 1st of February 2016 was in fact a Thursday. And our final thing then is we're just going to recode that day of the week into 3 categories using case when. And those are going to be Monday to Wednesday, Thursday to Saturday, and Sunday, making sure that's properly formatted as a factor. So our data set is ready to go then. We've got time of the week and day as categorical variables, and active vehicles and trips as continuous variables. Now, section 3 then takes us through both the individual steps for a chi-squared test and then how to implement that using code. Now, chi-square tests are applicable to situations in which we have proportions and more than 2 categories. So you might remember that so far the tests we've looked at are t-test, and this was applicable to when we had one numeric variable and 2 categories. We had prop test And this was applicable when we had a proportion and two categories. So chi-square then allows us to do something similar, but with a proportion plus greater than three categories. So three or more. And indeed, when we come on to do ANOVA in the next lab, that's going to give us the ability to use numeric data plus greater than three categories. So you can see between that then we've got numeric data in two categories, proportion in two categories, proportion in three categories, and numeric in three categories. And that will then just leave us with regression regression, which actually applies to two numeric variables. So what we're going to look at then is the proportion of days where trips were over 10,000 completed by a dispatch office, and look at whether they're statistically different between our 2 months, January and February. So actually in this example, we're just going to start off with two categories. Now, as we noted, the null and alternative hypotheses in this scenario are always specified in the same way. So if trips in January and February are statistically independent, that's our H0, our null. So the null will always be that the categories are independent of the proportions. So statistically independent. Conversely then, for H1, the outcome is always going to be that they are they are not statistically independent, i.e. there's a relationship of dependency. So it depends whether it's January or February if depot offices on average have completed a higher proportion of days where trips were over 10,000. So how does this work then? Well, firstly, we need to create that proportion variable. So we use if else here for trips greater than 10,000 for these two categories, and that's going to form our proportion. Now we can first look at this in a table, because really a table is what we run a chi-square test on. So we have January and February here, and not over 10,000 and over 10,000. So it's really just this 4x4 grid is all that we need for this kind of test. Let me do that a bit better. So our table then is January, February, and let's see which order it was in. So not over 10,000, so less than 10,000 and greater than 10,000. So our figures here then were 112 and 70 and 74 and 98. I'm going to put this up in the corner. So 117. Oh, no, 112 and 70, sorry. Let's try that again. So we've got 112 and 70 and 74 and 98. Now, what we also need for this then is that we need rows and column totals. So we need the sum of rows and columns and the overall sum. So if we come back to here, those were 182, 172, 186 and 168. And then, of course, our overall is 354. Now, the reason I've left some blank space here is what we're going to do is we're going to use these row and column totals to compute for each of these squares what we call the expected probability. Now, the expected probability is going to be what would happen if we shared out these totals such that there was no relationship. And we can then compare these actual numbers to that hypothetical number. So we'll come back to this, which is our code for this. I'm going to come down here and calculate these. So these are our expected frequencies for our different cells here. So expected frequency for each cell. And we can see we've read them in here. So we've got 186 and 182. So for this one, 182 and 168 would be for this cell. Let's put those into our table. We've got 95, 86. So our expected frequencies are 95, 86, and 90 and 81. So we can see then some of these are higher, so 96 higher than 74, and some of these are lower. So we've got a difference then between the observed frequencies and the expected frequencies. The next step then just allows us to compare those. So we take our expected frequency and subtract our observed frequency. We square it and we divide it again by the expected frequency. And this gives us what we call relative square deviations. So again, we get one of those for each of our columns. So 2.8 and 3.1. Go back to this. So our relative square deviations are 2.8, 3.1, and 2.9 and 3.2. Now our final step then is we just need our test statistic and we need to put that into the relevant distribution, which is p chi squared here. And actually our test statistic is super simple at this point. We just sum together these relative square deviations. And that gives us our chi-squared statistic. So that is 12.15. So again, if we come back to this, we've just got 2.8 plus 3.1 plus 2.9 plus 3.2, and that equals our chi-square. So this is the kind of calculation then that can, and historically was, basically done on paper. It's a relatively simple set of calculations that just takes into account the information in the table, row and column totals, and calculating for each square an expected frequency at a relative square deviation. The last bit then just involves degrees of freedom. And again, this is a simple calculation for this. So degrees of freedom in this test are, we have two rows and two columns. So our degrees of freedom is 2 for the columns, 2 for the rows, subtracting 1 from each and multiplying those together. And of course, this means in this example, we have 1 degree of freedom. Now, these degrees of freedom are important because in the chi-square test, as we can see here, the distribution differs a bit in terms of degrees of freedom. So where we're reading off our critical value is going to lead to a slightly different p-value depending on the degrees of freedom. For that reason, then we need to supply that information when we put it into the distribution. So we've got probability of chi-squared. Now, in this case, because we don't have to think about a direction, this is always going to be 1 minus p chi-squared. We use our 12.15 figure here and a figure of 1 for degrees of freedom. And we could note that 1 minus p chi-squared is exactly the same thing as lower tail false. And we would always do it this way around for chi-square. So our p-value then is 0.004. And obviously, as we know, that's a very low p-value. So with a p-value that low, is it lower than our alpha, which in this case was set at 0.1 or 10? Well, yes, it is. So that causes us then to reject the null hypothesis. So we reject the hypothesis that the month is independent of the proportion of trips over 10,000. In fact, it is dependent on whether it's January or February, whether we have a proportion of over 10,000 trips or a higher proportion of over 10,000 trips per observation. Now, one thing you might note, though, is that we just get a p-value here. So we saw our p-value is pretty close to 0. So p for this equals 0.00. But we don't get a lot of other information about this. We just have our p-value. So we know there's some relationship of dependence between here and here. But it's a little bit difficult to see what, and this is with only 2 categories on each side. If we had 3 or more, it gets more and more difficult to see where the effects are. Now, with a table like this, we could just look at a proportions table. So this should be for table 1, sorry. So we've got table 2 here. If I look at the proportions of table 2, I can get a good idea here of, okay, so not over 10,000, that has a higher proportion of that kind of day in January than in February. So I can see it's really that January has a lower proportion of observations with over 10,000 trips than February. So I need to look at the actual data then to see, in a sense, what my p-value means. My p-value for a chi-squared test just tells me there's some significant relationship of dependence between this variable and this one, but it doesn't tell me where. Now let's quickly look at doing this with the chi-square test function before we move on to an example with 3 categories. So this is the function chi-squared test, and fittingly for something that we essentially calculate on a table like this, we just need to give it exactly the same information that we would as a table. So we have one variable here and then the other, so just extracting the variables from the table using our extract symbol. And here we've just got correct set to false. Now this is because this matches the way we calculated it here. There is a correction though that we commonly apply to a chi-square test that makes it a little bit more reliable. So if we get rid of that, then that's really all we need for a chi-square test. You see this is called Pearson's chi-square test with the Yates continuity correction. If I'd left that how it was, then well, I'd get it without the correction. But let's just look at this. So again, we can see we've got a low p-value here. Our x squared was a little bit lower here. So this correction works by essentially subtracting a little bit from our difference in frequencies from each square. So it's going to cause us to have a slightly lower x squared and a slightly higher p-value. It's a more conservative version of the test. Now, for that reason, we can also run this on a table. So if rather than putting the 2 variables in here, I just put table, we can run a chi-square test on it. You can see with the correct, we get exactly the same p-value that we calculated before manually. So Pearson's chi-square test without the continuity correction. Or if I want to do it with the correction, I can just delete that. And that's my test. Now, in section 4 then, we're going to look at chi-square tests with multiple groups, which is really the use case for chi-squared, because unlike prop tests, chi-squared can handle multiple groups in the table. So how can a chi-square test work on multiple groups then? Well, if we go back to the logic of the test, it's fairly easy to see why. Because if we can calculate these expected frequencies for each square here, then the challenge doesn't get that much harder if we add another column. Because really all we're dealing with here, so say if I wanted to use, say, March here, well, I would have 2 more numbers here for March. I'd have a different number here, and I'd have 98 plus 74 plus x here, 112 plus 70 plus x. So adding another column then doesn't really change our calculations much. We just have different row numbers and 1 additional column total. And we would just repeat those steps again, generate a chi-squared statistic, and go on with our calculation. So how does that look? Well, let's look at day of the week. So earlier on, we calculated 3 categories for day of the week. So now we're going to say it's the proportion of days with over 10,000 trips and the day of the week independent, or is it not independent? And we can kind of assume that day of the week probably makes a difference because all other things being equal, we think the end of the week, Thursday, Friday, Saturday, people are taking more trips. So how does this look? Well, that would be our table. So we've got 3 groups now, and the proportion not over 10,000 and over 10,000. And we just put in that variable. And there we go. So we have our p-value again, and that's telling us that, well, the time of the week does matter. We reject our null hypothesis because we have a p-value below our alpha, which in this case we selected as 0.01, but that's going to be low enough to be significant under a number of different levels. And so we accept our H1. It does matter what day of the week it is for whether the proportion of days with over 10,000 trips. There is a higher proportion of days with over 10,000 trips. Now, you'll immediately see, though, that the problem that we had before, which is that we don't know where the difference is, gets more severe the more groups we get. So we could convert that into a prop table, and we could have a look at it manually. What we really want to do, though, is look at where is the significant difference arising. And to do that, what we need to do is essentially do multiple different tests for each possible comparison. So with 3 groups, Monday to Wednesday, Thursday to Saturday, and Sunday, we have 3 possible comparisons. Monday to Thursday to Saturday, Monday to Wednesday to Sunday, and Thursday to Saturday to Sunday. Now, what we can do with this then is this second test. So this is what we get from the extra package that we installed here. So our companion gives us this pairwise test of nominal independence. So if we come down to here and run this test, we see again, this just runs on a table. It runs on exactly the same way as the standard test. We do get some other options here, though. So we're setting these 2 to false. So this is for the Fisher exact test, which is similar to a chi-squared, but we would usually use it on smaller sample sizes than this. We're also setting g-test to false, and we're comparing across columns, not rows. We'll see why in a minute. In this example here, we also have this method set to none. Here you can see it set to Bonferroni. Now this would be the default, so we're going to do it this way just to see the results first. So you can see the comparisons here then. So we've got 3 individual 2-group comparisons within this test. We get a p-statistic for each of them and an adjusted p-statistic. And what we can see is that what's really driving our results here is the comparison of Monday to Wednesday to Thursday to Saturday, and to a lesser extent, the comparison of Thursday to Saturday to Sunday. By comparison, Monday to Wednesday and Sunday actually don't seem to differ too much. We have this much higher p-statistic telling us that broadly there's a high chance the null hypothesis here is true, i.e. there is no relationship of dependence for this pair. Now, usually, though, we would have this method set to the Bonferroni correction. And briefly, what this does, it will tend to make our adjusted p-values, so this is the method of adjustment, higher. Now, you might think, why do we want to do that? Why do we want something that's going to give us higher p-values? Well, we can see that if, for example, we have more categories. So we had time of the week here, but we also have day. That has 7 categories. So if I run this with day, that's 7 groups. And you can see that it immediately explodes the number of comparisons. So for 3 groups, we only have 3 comparisons, but for 7 groups, we already have 21 one-by-one comparisons. Now, to understand why we need to adjust this then, because here we can see that although we have some low p-values for individual day comparisons, so Saturday to Sunday here, all of our p-values have been adjusted upwards to the extent that none of these are significant anymore. Well, to understand this, we've got to think about the logic of statistical testing. So we know there's a level of possible error whenever we conduct a test. And thus, it's possible to get low p-values basically at random if we start running a large enough number of tests. So if I randomly split up my observations into 7 groups and ran this test, it'd be quite likely I get some low p-values. And we don't want just running a lot of tests to be the source of our results. So in a sense, this correction penalizes us for running too many tests of nominal independence at once. That it says that if we're going to run this many comparisons and look for a low p-value, we need a very low p-value to begin with to be actually sure that our result isn't a false positive. So this version then can be seen as a more conservative, with a small c version of the test. So it's going to generate, all else equal, much lower p-values in the much higher p-values rather in the adjusted than in the original chi-squared, because it's accounting for that fact that if I just run enough tests between any randomly selected categories, eventually I'm going to find a low p-value, and that's not what we want for robust social science. So that's the chi-squared test then, and the key thing really to remember, going back to what we looked at the beginning, is that this is about data structure. So if I have 2 groups and continuous or numeric data, I need a t-test. If I have 2 proportions in 2 different groups, I can use prop test. But if I have proportions and I have multiple groups, so I'm in this situation where this is my data, so 3 months and 2 categories within them, or indeed I could have more categories down here if I wanted, I'm going to need to use a chi-squared test. But we have this limitation that it's just going to give us a p-value, and so we need to follow it up with additional tests that make case-to-case comparisons across all the possible different categories. So I'll leave that there. In the next example, we'll look at ANOVA, which, as I mentioned at the beginning of this, allows us to do this same thing, use more than 2 categories, but instead of proportions on this side, it's going to be continuous data.